Welcome back to the lecture series on AC machines and transformers. In the last class, we discussed about armature reaction, effects of armature reaction, and how do we mitigate the armature reaction. This class, we will be talking about what is all about commutation and how do we improve the commutation process. In general, commutation is the process of changing current from one direction to other direction. In a DC generator, voltage induced is AC, that is alternating current. But we have to convert the AC voltage induced into DC. Why do we convert AC to DC? Because DC loads need a DC supply. What is AC signal? AC signal is basically an alternating one. Positive half cycle followed by negative half cycle. Positive half cycle, negative half cycle. We are plotting the waveform with respect to t, that is the time axis. X-axis is the time axis and y-axis is the amplitude axis. Maybe of V or maybe of a current I. In order to indicate alternating current or voltage, we use the small alphabets, which is function of time. Small v implies, you can understand this is V of t. Similarly for the current, meaning at every instant, at every time instant, let it be t1, t2, t3, and t4, t5, and so on. The value of current is changing. 0 to positive maximum, decreases, comes to 0, and increases negative maximum and 0. We have to convert the induced AC into DC. That is, we are converting alternating current into the pulsating DC, meaning DC current or voltage is a unidirectional. Positive, we are plotting with respect to time axis, and let the y-axis may be of a DC voltage or a current. Look at here, we are using capital alphabet. If we use the filter, through filter, we can convert this pulsating DC to a constant DC signal with respect to time. Maybe of capital V or current I. So current or voltage is constant with respect to time. So in order to indicate the steady state value or a constant value or a DC value, we use capital alphabet to indicate the steady state electrical parameters. Now the question is, how do we convert the alternating current or voltage into unidirectional voltage or DC voltage or current? For that, we need commutator. Referring our earlier discussion, commutator, I told it is a mechanical rectifier which converts induced AC voltage into DC voltage. Commutator is attached to the rotor, which is a rotating one. Commutator is also rotating one. The brushes make a contact with the commutator segments, and which in turn connects the induced voltage or current to the load terminals. So commutation is the process of changing current from one direction to other direction, and commutator is a device which will convert induced AC voltage into DC voltage. Commutation in a DC machine implies that the change that takes place in a winding element during the period of a short circuit by a brush. Alternatively, reversal of current in the armature winding by means of commutator segment and carbon brushes. We can call it as a commutation process. In a DC generator, when armature conductors are under the influence of north pole, which will carry current in one direction, say about a departing current, the same conductor coming under the influence of south pole, which carries current in the direction. You can say it is an approaching current. So current flows in one direction when armature conductors are under the influence of north pole, and in opposite direction when armature conductors are under the influence of south pole. So while conductors entering from south pole to north pole, current in the conductors are reversed. That is, from south pole to north pole or north pole to south pole, the current in the conductors are reversed. So where this reversal of current takes place, which is along the MNA axis or a brush axis. Brush axis is another name for MNA axis, magnetic neutral axis. The process by which the current in the short circuited coil is reversed while it crosses the MNA is called commutation. Let us discuss the process of commutation with the help of ring type armature winding. Ring type armature winding is a type of winding in which wires are wound around the inner and outer surface of a armature core. Armature core is basically of a cylindrical nature or ring type. Let us consider the width of the brush is equal to, that is the width of one commutator segment plus one mica insulation. Number of commutator segment, we can define number of commutator segments, yes, I write shortly, this is equal to number of conductors by 2, also equal to number of chains, equal to number of chains. We know each chain consists of two conductors, conductor 1, conductor 2, back end of the conductor and front end of the conductor connected to the commutator segment. Then another segment. So two conductors are conductor 1 and conductor 2. Two conductors are connected in a single commutator segment. Referring the figure, coil B is about to short circuit because the brush is going to have a contact with segment A. Where current 20 ampere comes this direction, because brush is not connected to the segment A, hence the current is not collected via this segment. So the current goes through the coil B, 20 ampere current, because the total load current is 40 ampere, and another 20 ampere is from the coil C. At this node combined together and it enters into the commutator segment B. So the total current becomes 40 ampere and via the brush which is connected to the load circuit. Case 1 indicates the coil B prior to short circuit. Referring case 2, 3/4 of the brush is in contact with the segment B and 1/4 of the brush is in contact with the segment A. We know the total load current is 40 ampere and 1/4 of the current is collected via commutator segment A comes to the brush, and 3/4 of the current, that is the 30 ampere, 10 from coil B and 20 ampere from coil C combined together at this node and collected to the brush through the segment B. Referring case 3, brush is equally in contact with segment B and segment A. There is no current flows through the coil B. So coil B 0 ampere. So from coil A 20 ampere it comes to A, and via commutator segment A it goes to the brush, and another 20 ampere via coil C come to this way, and via commutator segment B the brush will collect totally 40 ampere. Referring case 4, look at 3/4 of the brush is in contact with the segment A and 1/4 of the brush, there is only this much of the brush width is in contact with the segment B. So via segment A, 30 ampere current is collected by the brush. So 20 ampere from the coil A here and another 10 ampere from the coil B via this way, okay, to the segment A. Totally 30 ampere via segment A to the brush. And look at the current in the coil B is being reversed. In the earlier cases, it was from left to right. Now it is from right to left. Okay. And the current from coil C is 20 ampere, 10 ampere via coil B and another 10 ampere via segment B to the load terminal. So here 30 plus 10, totally 40 ampere current is collected by the brush to the load terminals. Look at the case 5. The commutator segment A in complete contact with the brush. So the coil A supplies 20 ampere and coil B supplies another 20 amperes. So the total load current is 40 amperes. Look at case 6. Via this path, 35 ampere current entering into the segment A and 5 ampere current via segment B through the air to the brush. It is mainly due to the self-inductance of a coil. The self-inductance of a coil will not allow the current to reduce its value immediately. What will happen? That leads to spark in the commutator segment and brushes. It leads to power dissipation. Figure 7 shows the current time graph of the commutation coil. I referred a couple of instances here because x-axis is the time axis. I am referring the time instance, namely instant 1, 2, 3 and so on. So prior to instant 1, 40 ampere is flowing or taken by the load, and look at the time instant 1, the current is started decreasing. Current is started decreasing. At instant 2, it comes to 20 ampere. Comes to 20 ampere. And at instant 3, it reaches 0 ampere. And instant 4, again it reduces to minus 20 ampere. Then at instant 5, it reaches 40 ampere. At C and D, it maintains the 40 ampere value. And look at the change happens very smoothly from 40 ampere to 20 ampere, 0 and minus 20 ampere, minus 40 ampere. So this is called as, this process of smooth commutation is called as a linear commutation, and time Tc is a commutation time interval or simply of a commutation time. And due to the self-induced EMF, immediately it will not reach the value 40 ampere at this point. It will reach 35 ampere and it takes another time to reach to 40 ampere. As I told, this pink color graph is called as an ideal commutation. And this one is the dashed line current time graph of a commutation coil is called as a non-ideal commutation. Look at point E, only 35 ampere, minus 35 ampere it reached, and it takes another time to reach the, there is another 5 ampere it takes some more time to reach its zero value. That is what earlier I told. Self-induced EMF in a coil will not allow the current to reach at this instant E. It takes some more time. At this instant, the current is completely comes to 40 ampere, minus 40 ampere. How do we improve the commutation? Basically, there are two types. One is the resistance commutation, another one is the EMF commutation. Current in the coil C reaches the press via two parallel paths. This parallel path number 1 and so path 1 from coil C comes to the commutator segment B and C press. This first parallel. Second parallel path via the short circuited coil B, because the current direction is reversed, we call it as a short circuited coil, and segment A and to the press. Brush, we know we can use two types of brushes. One is a copper brush, another one is a carbon brush. If it is a copper brush, the current will follow the first path, this path. If it is a carbon brush, the current will follow the second path. Let us assume the first path resistance R1 and the second path resistance 2. So the brush contact area with segment B is decreasing and brush contact area with segment A is increasing. We know R is equal to rho L by A. Area increases, resistance will be decreasing, and if area decreases, resistance will be increased. R is inversely proportional to area. So the path 1 will offer more resistance and path 2 will offer less resistance, and the current will flow through path 2. The merits of the carbon brushes are some degree of self-lubricating and polishing the commutator, and the damage during sparking is less compared with the copper brush. The drawbacks are contact drop is high, that is nearly about 2 volts, and the size of the commutator is larger than using the copper brush for efficient heat dissipation. The another way we could improve the commutation process is called as a EMF commutation, in which the reactance voltage is neutralized by producing a reversing EMF in the short circuited coil under commutation. So this reverse voltage is basically out of phase to that of the reactance voltage. There are two methods used for this purpose. One is about the interpoles. We have discussed during armature reaction. You refer previous lecture. And the second method is to through brushes are forward shifted to bring the short circuited coil under the influence of next pole of opposite polarity. So far, we have discussed about process of commutation and the role of commutator in a AC generator. Also, we understood how the commutation is taking place with the help of several diagrams. We also discuss about the techniques used for improving the commutation, namely the resistance commutation and EMF commutation. The next class, we will be dealing with the parallel operation of generators. Thank you.